Yeah, just before get going, can you see my screen in a full screen mode?
Yes, we can.
Okay, perfect. So, greetings, everyone, and I would like to welcome you to this presentation in which I will give you a very brief overview of some of the research undergoing within our BRIMM network, which comes in partnership with our multi-institutional partners, including McGill University. So John did most of the introduction. Thank you, John. Briefly for myself, my name is Madiseh. Currently, I'm an assistant professor in the mining engineering department at UBC. I also hold Canada Researcher in Advanced Mine Energy Systems. That means that the focus of my research is in mine energy, mine mechanical, and renewable energy systems. I will act as BRIMM Sustainable Mine Energy Systems theme lead. Let's look at some of the challenges that mining industry is facing with regards to its energy consumption. The first challenge is the energy costs. This is a figure by US Department of Energy, still very relevant, although a little bit dated. So you could see that most of our natural resource industries, including mining and petroleum, are amongst the most energy intensive industries, meaning that to generate 1 unit of revenue or $1 contribution to our GDP, they would consume a lot of energy overall in BTUs. And that's why with the extent of these operations, they are consuming a lot overall. That's why energy costs represent something like 15 to 25% of our production cost overall across the board in different mining applications. I'm giving you an example of a Canadian mine. It's a remote mine from Northwestern Territories. This is a fact sheet printed out by the mine to give awareness towards energy conservation and overall carbon emissions at mine site. It is a fantastic wealth of information. You could see that this mine, because it's remote, it's using diesel for almost everything. 44% goes to fleet, 43% for power generation in the diesel gensets, and the majority of the remaining set of energy stream is going towards heat because it's Canada and it's cold. That's why overall this mine is using something like 75 million liters per year. If you imagine Canada has only 30-something million population, it's a lot of consumption for only single mine. And in very bold capital letters, they're telling us that 20% of their operating cost is energy, which sits very well within that range. The second, but maybe even more challenging and more serious challenge is environmental footprint. First of all, diesel particulates and other emissions found at mine sites, especially in underground subsurface operations, are being classified as carcinogenic. So these are curtailment and removal is a must in the near future. But more importantly, carbon emissions are becoming a more and more pushing factor in transition towards decarbonization. For example, in Canada, there is a plan called a Healthy Environment and a Healthy Economy Plan, under which it is perceived that by 2030, carbon tax would go from its current almost $40 per ton to almost $170 per ton, which means that every liter of diesel would be more or less 38 cents more expensive at these mine sites. Not only that, by 2050, we need to get net zero carbon. That's why decarbonization has become an existential question and challenge for mining. So let's look at what IEA, International Energy Association, is telling us with regards to what will evolve and how this transition to zero carbon would roll out. So by 2030, it is perceived that the share of the current technologies available in the market, basically off-the-shelf technologies, is quite significant, something like 80%. And there is like 15% of the solutions that will be the result of R&D being developed, maybe midway through the R&D pipe. They will be developed by that time, 2030, which is only 8 years away, right? From the time that we are looking at these things, by the time we get them to the shelf and the OEMs can manufacture it and have the supply chain for it, it's going to take a lot of time. But what is really important is to remember that by 2050, the share of solutions that are being developed or has to be developed basically is going to grow quite significantly, almost 50%. So R&D is needed in a level that is unprecedented. Now the question is, are we going to adopt them, wait for them to be developed, or partnership or are we going to develop them in partnership with other institutions and OEMs and so on and so forth? That's a big question for mining to answer, but there is an array of solutions that are being looked at for those kind of R&D solutions that are being, and technologies that are being developed. They include, for example, renewables. They have a fair share to play, as John showed in his second slide. Also, there are storage solutions, electrochemical for power, thermal for heat, and also other solutions, for example, pumped hydro, which is basically going to let you do peak shaving, so on and so forth. And also, there are digital solutions. So whatever we do, these solutions, the array of solutions that we are looking at, will need to be site-specific and customized, because there is no single bullet, or as John put it, there is no one-size-fits-all solution. Surface mines are not like underground mines. Hard rock mines are not like soft rock mines. Grid access is very important. If you're in a remote and off-grid location, your energy portfolio is going to be totally different. Climate is an important factor, and cold Arctic mine is not like a mine that is located in a hot and humid environment. And also comminution and mineral processing. So whatever is happening on the surface or underground as part of that comminution beneficiation processes, it is going to play a very significant role. And all these solutions, like pieces of puzzle, have to sit together to give you a mosaic of solutions, hybrid and integrated. In the end, it is also perceived that all these solutions are electrified and digital. They're in connection in a smart network and will interact actively. Today, I'm going to pick a few examples. I'm going to focus on some of the thermal solutions that are being developed in our network. So those are going to highlight the thermal and rock mass storage. Mine energy digital twin would address all these highlighted in red areas like renewables, electrochemical storage, thermal storage, and digital solutions. And in the end, I will end up with UBC Hub, which is a very significant infrastructure at UBC, being developed at UBC, that will address these areas. So let's start with the lowest hanging fruit. For me, that would be waste heat recovery. So any off-grid mine will have these diesel generators, a few of them. It is very common to find 10, 15 megawatt power of power capacity installed at a remote mine site. And those who are involved in this technology know that for every unit of electricity that you produce, you're going to reject 2 units of waste heat. So the idea, which is not really a novel idea, it has been implemented in other locations. And this is an example of one of those readily available off-the-shelf technologies that mining has to adopt more and more. And will play a role within from now on till 2050. So when you look at it, the waste heat is a valuable source of energy that we're just rejecting, right? So what if we could use a heat exchanger, a large-scale heat exchanger, to recover that heat and then deliver it? Maybe the novelty of this solution that we are devising here at UBC is that we are intending for that heat to be used in the intake air heaters. So subsurface facilities need intake air heating, especially in cold climates like Canada. So that is a big consumer of heat on mine sites. So we have devised a smaller scale system which has 2 parts: air capture on the left, heat capture on the left. So recovering waste heat in the heat exchanger. So you could see that red box sitting below this frame is the generator. My students are running the test outdoors. So the generator is giving you the waste heat, and then you're delivering it to this unit, which is basically equipped with an AC air conditioner, providing you with cold air, and the heat is delivered to that cold air. This is a small replica of a larger scale system in which the mine intake air heating system would be just the delivery side of it. So our research is showing that in every mine you have a set point. For example, in this example, I have 1.5. Whenever the ambient air temperature is below that, you have to fill that gap, bring that temperature, upgrade that temperature to the set point, for which you have to, currently most mines are using some sort of a fossil fuel. Some mines are doing very smart ways of preventing that, but this system will help basically filling that gap, and then the potential savings are around $1 million. When you look at it, this is a very mature technology that you can adopt into your, integrate into your mine, and then save a lot of energy and also prevent carbon emissions. But the question is, what about the summertime? In the summertime, there's no need for that intake air heating, but the waste heat will be rejected anyway, right? So you can increase your storage capacity by building something like a rock pile thermal energy storage. And this is one of those, again, research partnerships that examples that we have. So we're working on these larger scale rock pile storage systems that will recover the heat, save it in the rock mass sitting in that rock pile, and then in the winter you can tap into it, and you have additional thermal power that you can take advantage of. The challenges in designing these things are very complex, porous medium, heat transfer, fluid mechanics phenomena that you have to master, but it has been done. We have been able to get very good results, and we are further developing it in partnership with industry. Maybe the second area of focus is electrification. Well, electrification is a key factor in decarbonization. You can have a mine that is using 100% renewable electricity, but because its materials handling fleet is still using diesel, its carbon footprint has not improved that significantly. So that's why OEMs are working, like these are some examples on the lower left of the picture. So some of the examples on battery electric fleet and also hydrogen electric fleet that is being developed. But when we look at that, and those come, let's not forget, those come at very good, like considerable health and ventilation benefits. So you are removing diesel emissions, reducing noise and heat. You're also lowering the ventilation duties, so fan duties, and not only the flow, but also more significantly power. So overall energy cost, ventilation costs, and also you're reducing mine heat loads. In hot environments, diesel equipment underground are basically a very significant source of heat, and you don't want it there because then you have to pay for it and cool the mine. But more important is to understand that replacing diesel fleet with electrified fleet is not the only solution. There are also a variety of electric materials handling solutions. On the right, I'm showing you, for example, the RobCon and also the Railway. These are very good candidates, if possible, if implementation of those solutions is possible. They are very good candidates to be used in hybrid, for example, with your mine fleet. Here within our network, we're working on maybe further down the road, more under research kind of solutions as well. One of them, which is a key, if you look at it, most of these bigger players in mining, like BHP, Anglo, and so on, they all have an envisioned continuous mining machine. That's why OEMs are working on it. The challenge in them, and they come at very good positive points. Like on the positive side, they are fully electric, they're continuous, not batch, and also they follow the ore, so it's selective mining. There's less dilution and also less waste. However, on the downside, there is high wear rate and high energy intensity. So what we are working within our network, and I should mention, this is a very healthy and also very full contact partnership between UBC and McGill. So McGill has a big role to play in this research. And also we have very good partners that are working with us hand in hand to develop these technologies. But the technology that we are working that will help these continuous miners is microwave assisted rock preconditioning. So when you precondition the rock, whether on the face, you would reduce the rock hardness. So this continuous miner would see a rock that is dealing with a much basically a lower hardness. And then it can, the wear rate and the energy consumption would drop. Or if you use it either on the face or in the mill, downstream in the comminution, you would have better liberation, and that improves the comminution and liberation and lowers the energy consumption, especially electricity consumption, quite significantly. Moving on to the mine energy digital twin as an example of integrated hybrid solutions for decarbonization. Let's go back to our good old friend, that mine from Northwestern Territories. This is a surface mine. So comminution and mineral processing have a significant role defining the energy portfolio of the mine. For example, you can have minimal comminution mineral processing to intensive, and it changes the portfolio of energy consumption. If you replace the diesel system with a hybrid system, you could have fuel cells, hydrogen fuel cells, and hydrogen basically being used for electricity storage or battery, or you can have a combination of all of them, of both of them. In the fleet, you could have battery electric fleet, BEFs, or you could have hydrogen power fleet. What we are developing is basically, I would like to envision it as this tool that is a digital tool that will let you incorporate all these factors in and then arrive at the best solution. There is a very significant level of optimization and also data incorporation, data fed to this system, and it will show you, like I'm showing you a radar map as an example here, that, for example, that more intensive and less intensive comminution, two extremes, where are they sitting? And in fact, our data is showing that, our results are showing that hydrogen fleet can be a better solution for these surface mines with very large materials handling requirements. And the same should be done for any case. And that's why we said there is not a single bullet. It is a very custom fit design for every mine. I would like to end with an opportunity here. NUBC, we have been approved to get a UBC $23 million hub developed. At the end of the development, it will be a fantastic tool. The reason is it will have 100% renewable electricity that is generated across this microgrid. And it is equipped with a hydrogen system, the water electrolyzers and hydrogen storage system, and fuel cells that would basically allow us to generate 100% renewable hydrogen. Every member of this network, whether it's a producer or like a vehicle or whatever, it's a smart member. So there is active energy transactions, for example, between the fleet and the network, and they're all 5G enabled. So this will enable us to have very rigorous data analytics and optimization and basically digital tools at our disposal to optimize the utilization of the system and arrive at the best design, best performance. So it will be a unique research asset for pilot scale implementation of future mine energy systems. With that, I would like to pass it on back to John, and if there are any questions, I would be happy to answer them.
Thank you, Ali. That was a quick, a lot of ground and covered very quickly. But I hope that it gives a view of the different types of expertise that UBC has. We might move on to the next speakers.